for the introduction of MOS. A metal oxide semiconductor, or MOS, is a semiconductor device in which a metallic oxide serves as an insulating layer, such as silicon dioxide. Generally, the MOS structure is obtained by inserting an insulator layer between a metal and a semiconductor. MOS structures are essential for a wide range of semiconductor devices. The metal semiconductor solid-state device was discovered in 1874 and referred to as a whisker contact rectifier, which included a wire tip press into a lead sulfide crystal. Ever since, these devices continued to capture great attention in monitoring and testing due to their low cost, high sensitivity, and simplicity. But over time, it was improved and the wide range of metal semiconductor junctions and its application highlights its significance. Metal oxide semiconductors are valence compounds with a high degree of ionic bonding. Their conduction band minimum and valence band maximum mainly consist of the metal Ns and oxygen 2p orbital, respectively. In general, the metal Ns orbitals are highly dispersive while the oxygen 2p one is localized, which results in smaller effective mass for electrons compared to holes. In order to achieve p-type conductivity in metal oxides, the hole effective mass should be significantly smaller. Next, for the basic concept, the MOS structure can be viewed as a PN diode with one heavily doped side, that is the metal, and an extra insulating layer. Under a forward bias, the insulating layer blocks diffusion, so the depletion layer narrows, but there is still no vertical current. In the MOS structure, an oxide layer separates the metal and semiconductor from each other. For instance, at the metal/insulator interfaces, there is a continuous distribution of surface states with energies located in the bandgap of the semiconductor. The intermediate oxide layer helps prevent the diffusion of the metal into the semiconductor but also alleviates the electric field reduction. The MOS is the most effective device for semiconductor surfaces based on their practicality, reliability, as well as stability for different surface conditions. Shown is the metal oxide semiconductor. It has a p-type substrate with a thin oxide layer and a top metal contact, also known as the gate. A second metal layer forms an ohmic contact to the back of the semiconductor, also referred to as the bulk. There are three different bias voltages. First, below the flat band voltage, VFB, between the flat band voltage and the threshold voltage, VT, and larger than the threshold voltage. These bias regimes are called the accumulation, depletion, and inversion mode of operation.
Traditional metal oxide semiconductor MOS structure is obtained by growing a layer of silicon dioxide (SiO2) on top of silicon substrate, commonly by thermal oxidation and depositing a layer of metal. As the structure silicon dioxide is a dielectric material, its structure is equivalent to a planar capacitor with one of the electrode replaced by a semiconductor. Conventionally, the gate voltage at which the volume density of electron in the evasion layer is the same as the volume density of hole in the body is called threshold voltage. When the voltage between the transistor gate and the source VGS exceeds the threshold voltage VTH, the difference is known as overdrive voltage. The MOS capacitor structure is the heart of the MOSFET. Consider a MOS capacitor where the silicon base is of p-type. If a positive voltage is applied at the gate, holes which are at the surface of the p-type substrate will be repelled by the electric field generated by the voltage applied. At first, the hole will simply be repelled and what will remain on the surface will be immobile, which is negative atom of the acceptor type, which create a depletion region on the surface.
So I will explain about the working principle of MOS. To understand the different modes of an MOS capacitor, we now consider three different bias voltage. First is below the frontband voltage. Second, between the frontband voltage and threshold voltage. And third is larger than the threshold voltage. So for the first principle is accumulation. It is occurs typically for negative voltage and where the negative charge on the gate attracts holes from the substrate to the outside semiconductor interface. This explanation were based on the shown figure. So for the next principle is depletion. It is a positive voltage. So positive charge on the gate push the mobile holes into the substrate. Therefore, the semiconductor is depleted of mobile carriers at the interface and a negative charge due to the ionized acceptor ion is left in the space charge region. And the voltage separating the accumulation and depletion regime is referred to as the flame band voltage, which is VFB. And lastly, for the inversion, it exists a negatively charged inversion layer at the outside semiconductor interface in addition to the depletion layer. This inversion layer due to the minority carriers that are attracted to the interface by the positive gate voltage. So that's all from.
Alright, so we proceed for the next topic. My name is BALQIS binti ISMAIL RANI with metric number 207782. Alright, so I will talk about home appliance for MOS, MOS capacitor, which is we have found is CCD camera. Okay, so just think of it as a CCTV. So there are many cases happen because of robbery surrounding our home, or office or workplace, hence where we have valuable things in there. So we must get to know our CCTV so we know which one is the best for our safety. Alright, so CCD camera is actually a video camera that contains a charge coupled device, CCD, which is a transistorized light sensor on an integrated circuit. Alright, so in plain English, CCD device convert or manipulate an electrical signal into some kind of output, including digital values. So in cameras, CCD enables them to take in visual information and convert it into an image or video. So they are, in other words, we call it as digital cameras, where we take a Polaroid. So this allows for the use of cameras in access control systems because images no longer need to be captured on film to be visible. Alright, so to be more detailed, CCD is a light sensitive metal oxide semiconductor, which is MOS capacitor, which has three components consisting of a metal electrode, or we call it a circuit, an insulating film of silicon dioxide, and a silicon substrate. So most capacitors are segregated into two classes of device, which is one having a surface channel structure and the other having a fluid channel design. It is the latter device that is used in the fabrication of modern CCDs due to several advantages of the fluid channel architecture. So the MOS capacitor array is fabricated on a P-type silicon substrate, which is as shown in the figure, in which the main charge carriers are positively charged electrons, which is we call it as holes. So prior to the multi-step photolithography-driven CCD fabrication process, a polished silicon wafer is bombarded with boron ions to create channel stops that localize integrated charge within the confines of a single pixel gate set. Alright, so the next step is in the fabrication process is to create the buried channels by implanting phosphorus ions in areas that will eventually be covered by polysilicon gate electrodes. So the N-type semiconductor formed by phosphorus contains negatively charged electrons as the primary charge carriers and forms a PN-type diode structure, which it serves to localize potential wells deep beneath the silicon dioxide interface. So as you can see from the figure is a schematic drawing of the diode structure. So the primary function of the buried channels is to localize integrated electrons away from the silicon dioxide interface, where they can become trapped during charge transfer. So by localizing charge deep within the P-type silicon substrate, transfer of charge occurs more efficiently with a minimum of residual charge remaining in the gate. So after the buried channels are formed within the silicon substrate, a layer of silicon dioxide is thermally grown on the silicon wafer surface to provide an insulating base for the gate electrodes. So next, a phosphorus dope layer of polycrystallized silicon, which is called as polysilicon, about 5,000 angstroms thick is grown on top of the outside layer. So this layer of polysilicon comprises the gate electrodes. We can see from the figure, and it is actually transparent to visible light, so making it an ideal substance for use in CCDs. Although the fabrication of a complete CCD takes additional steps, the basics of the MOS capacitor assembly have been completed at this point. Alright, so how does a CCD camera actually works? So from we can see from our workplace or our office or our neighborhood, we see that they use a CCTV at their house. So in terms of the working principle of CCD cameras, these video cameras actually capture an image and transfer it to the camera's memory system to record it as an electronic data. So CCD cameras' main accomplishment is the production of quality image without any distortion. So we could see a clear image. So we get past to anything. So basically the camera turns light into electricity. A CCD camera forms light sensitive elements called as pixels, which is we can see high resolution, the clearer the image is. So which sit next to each other and form a particular image. So CCD cameras have been in production for a long period of time, and then they have a high quality pixels that produce a higher quality, low noise image than any other camera. Alright, so as for the conclusion, for many years, so CCD has been the best imaging sensor scientists could choose for their microscopes. So a CCD sensor consists of two-dimensional grid of metal side semiconductor capacitors that we had exposed in this video. So like miniaturized rain buckets, the capacitors collect incoming photons and convert them into electrical current, which is sequentially read out and reassembled into a picture. However, a newer technology called as the complementary metal oxide semiconductor, or we call it as CMOS sensor, also known as the active pixel sensor, has emerged in a microscope of this marketplace. So the pixels in a CMOS sensor are slightly more complicated than those in a CCD, because each pixel contains not just a photodiode, but also a set of tiny transistors to amplify the light generated electrical signal and pass it along for processing.